Hello, and welcome to part 2 of hypothesis testing with one sample z-tests. So today we are going to be going over an effect size known as Cohen's d to look at the differences between our groups that we have measured with our one sample z-test. But as a refresher, let's go over that example problem from last time where we're comparing how often vegans mention their diet in comparison to the average regular American population. So keep in mind that the average American mentioned their diet 14 times a day with a standard deviation of 6. Now the average American mentioning it 14 times a day with a standard deviation of 6, that was the population. So that is characterized as mu equals 14 for the population mean of the average American, and sigma equals 6 for the standard deviation of the population for the average American. Now, when we took, when we took 100 vegans, that was our sample size, so n was equal to 100, and our sample mean for that, you can write that as x bar, or you can write that as a capital M, however you want to do it. But the sample mean equals 15.5. So this sample of 100 vegans mentioned their diet 15.5 times on average between those 100. So we did that. So step 1 was to state our hypotheses. So we had to mention our null and our alternative hypothesis. So our null hypothesis is always going to say the mean is 14. So the population mean for vegans, keep in mind we have the sample mean for vegans, and we're trying to use this sample to generalize to the population of vegans. And we do that by comparing it to the average American population, the population mean and standard deviation that's been provided to us. So our null hypothesis states that vegans are going to mention their diet at the same rate as the average American, 14. So null hypothesis is mu equals 14. The alternative hypothesis, again, we had to look over the question for that. So you have to read to determine if it's any indication of a direction. So, oh, we hypothesize that vegans will mention their diet more or less, but keep in mind for this problem, they didn't mention any specific direction of being higher or lower than the average American population. So it was just not equal to. Whenever it just says, oh, we want to look at to see if there's a significant difference or if they're not the same. Again, you're not really saying, oh, if they're higher or if they're lower. So when you have that vagueness in terms of difference, just a moment. Sorry about that. So, so our alternative hypothesis is saying that the vegan population does not mention their diet at the same rate that the average American population does. So our alternative hypothesis is that mu does not equal 14. Okay, so that was step 1. We walk out of step 1 having 2 hypotheses, the null and the alternative. Now, for step 2, that is where we determine the level of significance. We set the criteria. Now, the question itself, the problem itself mentioned that alpha was set at 0.05, which is our level of significance. Now, if you recall as well from last lecture, to find the critical values for your z statistic, you can look at that table that was included, where if it is a two-tailed test, which, by the way, this test is two-tailed, because it is not equal to. If it was indicating a direction, because our alternative hypothesis was not equal to. If our alternative hypothesis was greater than or less than, then that would be a one-tailed test. Since we're going in one direction, we think the significance is going to be in one direction, but it's not. We think it could go either way, so it is a two-tailed test. So with a two-tailed test with alpha set at 0.05, the critical values for z are plus and minus 1.96. Okay, so that's what we get from step 2. Now we get into step 3, which is calculating the test statistic itself. So calculating our z-score. Now with that, we had a couple formulas where first we have to find the standard deviation of the sampling distribution of the means. And that was sigma divided by the square root of our sample size. So we got 6 for sigma divided by the square root of 100, our sample size, and that gave us 0.6. Now that we have that, then we can plug that number into the equation to get the z-score itself. Amelia, keep your voice down. So we have sample mean minus, or excuse me, we have sample mean minus the population mean divided by the 0.6, the standard deviation of the sampling distribution of the means. So with that, we'd plugged in our numbers, 15.5 minus 14 to do our sample mean minus population mean, divided by the 0.6, again, the standard deviation of the sampling distribution of the means, and that gave us a z-score of 2.5. Now we use, to find the p-value, we use that 2.5 and we go to the z-table as we're accustomed to, and we always look at column C when we're looking for the p-value. So with that, in column C for 2.50 for the z-score, the p-value there is 0.0062. But since this is a two-tailed test, since our alternative hypothesis is saying it is not equal, we would multiply that value that we found in the C column of the Z table by 2. So our p-value is not 0.0062. It's actually 0.01. I've rounded it to 2 decimal places. Once we multiply 0.006 by 62 by 2, we get 0.01 rounded. Okay, so our p-value is less than alpha. Keep in mind that our alpha was set at 0.05. So our p-value of 0.01 is less than alpha, so we would reject the null hypothesis. You can also look at the z-score itself, that 2.5 that we obtained, and compare it to the critical values. Remember that was plus minus 1.96, which we obtained through that table that I showed you in the previous lecture. So since our positive z-score is greater than the positive critical value that's been provided of 1.96, that would also tell us that we're rejecting the null hypothesis. So we rejected the null. So what does this mean for the population of vegans? Well, that's telling us that the vegan population does not mention their diet at the same rate as the average American. So we had a sample of 100 vegans. We don't know about the population of vegans. We only know about the population of the general American public. So we use a one sample z-test to give us information about the population of vegans. Again, that was saying, since we've rejected the null hypothesis, we've rejected the idea that the population of vegans mentions their diet at the same rate as the average American. We're not saying that. We're rejecting that notion because that was the null hypothesis, that they mentioned them equally. So now, again, like I said, the vegan population does not mention their diet at the same rate as the average American. That is what we can conclude from this one sample z-test. Now I've written it out as well. Giving you guys the opportunity to pause your video so you can look at that screen. I don't want to just hold it up for like 2 minutes because you have the ability to pause the video. But you know, think about what the hardest part of hypothesis testing was for you. Was it the steps, you know, trying to make sure you get the steps down correctly? If it was, step 1 of, you know, stating your hypothesis, step 2 of setting your criteria, 3 of obtaining or calculating the test statistic, and then step 4 is making a decision. So do you reject or retain the null hypothesis? Those steps are going to stay with us as we continue on with all the tests that we're going to do, with all the t-tests, ANOVA, correlation, etc. We're going to be using those 4 steps. Was it determining what goes where? You know, how do I know that this is the population, or how do I know this is the sample mean? Those are usually clearly stated in the question. So whenever you see stuff like, oh, 100 vegans were sampled, Okay, well, I mean, it kind of gives it away when it says they were sampled. That gives it away that that is your sample of vegans. But whenever you see a number of people that were surveyed or, you know, involved in this study in some way, oftentimes that's going to be a sample. Oh, 100 people were surveyed. Likely that's going to be a sample because we don't really have the whole population number. We don't really have, we're not really sure exactly the number of, at least not, I personally don't know off the top of my head the exact number of people that live in the United States currently. And even if I were to Google that, there's a chance that there's a margin of error there. So someone was just born right now, boom, suddenly our population has increased. So there's going to be a little, you know, we don't always have the exact number of the population. So oftentimes when you're given a number of people, that's going to be your sample. If you're confused about what it means to reject the null hypothesis, or like, okay, so I understand, you know, I plugged it all in, I know how to calculate Z, I got 2.5, did that, cool. And I know that I reject the null hypothesis because my p-value is low, it's below 0.5 or 0.05. But I'm just kind of having trouble understanding the explanation. That also comes with time, or at least with more practice. But keep in mind that what we're doing is comparing vegans. We have a sample of vegans in this question, and then we have the information on the population of Americans in this question. Well, we want to find out more about the vegan population. All we have is the sample. We don't have the population of vegans. So what we're doing with this is that when we're rejecting or retaining the null hypothesis here, we're saying, hey, this vegan population, are they different from the general public population? You know, are they different? Are they going to mention their diet at a different rate than, you know, the average American? Now we're comparing all vegans. This question isn't necessarily clear about, is it like the vegans in the United States? I guess we can go with that. It doesn't really matter too much. But all the vegans in the United States, the population being whatever that number is, we're trying to find out if that population of vegans, if they mention their diet at a different rate than the average American. And that's going to be the case with all one sample Z tests. We're always going to have a sample of 100 or 50 or, you know, whatever your sample size is. And we want to know more information about the population that that sample has been taken from. So if you have questions, I still have my office hours. So, you know, don't hesitate. I know consultations are done at this point, at least for points, but I still have office hours to where, you know, the purpose of those consultations was to get you guys comfortable coming in to talk to me, knowing that you could come in to talk to me if you had questions. So if you're struggling with this, don't hesitate to come in. Okay, so I mentioned how this video was going to be talking about measuring effect size and Cohen's D. So with that, what is that? So when we measure effect size, we're looking at the difference between the sample mean and the population mean stated in the null hypothesis. So that sample mean of 15.5, those were the mean number of times that those 100 vegans that we sampled mentioned their diet. And the population mean was what just the general average American, how many times they stated their diet in a day. That was 14. So it follows the same rate as significance, or it follows the same suit as if we reject the null, it's significant. If we obtain the null or retain the null, then it's not significant. So just like how you have statistical significance when you reject the null hypothesis, and you do not have statistical significance when you retain it, same thing for the effect. So it doesn't matter how large or small your effect size is. If you reject the null hypothesis, that effect is significant. If you do not reject the null hypothesis, if you retain it, then the effect is not significant. So with the previous question, with our vegan question, comparing the vegan population to the general public, we rejected the null hypothesis. So when we calculate Cohen's D, that's going to tell us, no matter how large or how small it is, Since we rejected the null hypothesis with that initial test, with our one sample z-test, and we obtained the z-score and the p-value, etc. Since we rejected the null there, that's going to tell us that whatever effect we get, whatever effect size we get for Cohen's d is going to be significant as well. So how do you do it? Well, there's a formula, of course, but what Cohen's d is it's actually measuring the number of standard deviations that one mean has shifted above or below the other. So we're going to be using Cohen's d a lot. We're going to be using it with pretty much most tests that we do from here on out. And it's going to slightly shift in terms of what it means in terms of, the population mean and the sample mean. But for the most part, the premise is the same. So it's just the number of standard deviations apart that our two means are. So we have our mean of 14 for the population, and we have a mean of 15.5 for our vegan sample. That was the sample of vegans. So here you see the formula where we're doing sample mean minus population mean divided by the population standard deviation. We have all those numbers. I did mention before in the last video that it's easier to just write all of the stuff that you know to the side. Amelia, keep your voice down, please. So it's easier to write all the stuff to the side, because then when you have Cohen's d or any formula, you can just easily plug that in. So Cohen's d can be it really can be any number. It can be large or it can be small, doesn't really matter, because it's just measuring the number of standard deviations apart these two means are, our population and our sample mean. So you can have means that are like 7 standard deviations apart. You can have some that are 0 standard deviations apart. They would just be, the same mean twice. But it can be any positive or negative number. So with that being said, let's actually calculate Cohen's d for our vegan equation, for our vegan sample or example. So we take our sample mean minus population mean and divide it by our population standard deviation. So we have our sample mean of vegans of 15.5, our population mean of the general American public being 14, and the standard deviation of the general American public being 6. So 15.5 minus 14 divided by 6, that equals 0.25. So Cohen's d equals 0.25. Okay. So since we rejected the null hypothesis, again, we've already done this equation. I'm just tacking on the effect size. But since we did reject the null hypothesis that vegans and the general public mention their diet at the same rate, we know that our effect size of 0.25 is also significant. So what does this even mean? Why are we doing this? I mentioned how, there's standard deviations apart. How does that work? So our Cohen's d was 0.25. That told us that the observed effect shifted 0.25 standard deviations above the population mean. So we had our vegans at our sample mean of vegans at 15.5, and that is a quarter of a standard deviation higher than the population mean. So we take our standard deviation of 6. If we divide that by 4 to make a quarter, so 6 divided by 4 is 1.5. So 1/4 of a standard deviation is 1.5. You'll see that our sample mean of 15.5 is indeed 1.5 higher than our population mean. So when we're saying, Cohen's d equals 0.25, that number actually does tell us something. Again, since 0.25 is 1/4 or 25%, it's saying that 25% of our standard deviation, that's how much higher our sample mean is than our population mean. And it's true. If we did 15.5 minus 14, we'd get 1.5. And that is a quarter of our standard deviation. So if you're just kind of wondering what that number means for Cohen's d, that is breaking it down. Okay. So Now, when we graph Cohen's d, typically when we graph Cohen's d, we use a bar graph. We're not really going to be dealing with histograms much. I know that's like an old word at this point. That was like weeks up, probably about a month ago at this point. But now we're sticking to just standard bar graphs. And so when we depict the difference, when we depict the differences between groups like we do with Cohen's d, typically we're going to do that using a bar graph. So you'll see here that we have a bar graph of the average number of times the American population mentioned their diet and the average number of times that our vegan sample mentioned their diet. And we just graph that, and that's how you display Cohen's d, just by comparing two graphs or two bars on a graph. So in terms of the effect size itself, that number that spits out of the Cohen's d equation, well, we have a threshold of strength for that. So if your Cohen's d, and this is just the number, if it's a positive or negative, don't worry about that in terms of determining the strength. A positive or negative is going to be whatever strength that the number is. So if you have a negative 1.5 Cohen's d, don't think that that is a small effect size because it's less than 0.02. It's a large effect size. But let me kind of go over this graph a bit. So again, looking at just the number itself, not the plus or minus, just the number, you're going to see that if your Cohen's d of just the number is 0.2 and below, or well, 0.2, less than 0.2, it's going to be small. So if you have a Cohen's d of negative 0.19, if you have a Cohen's d of 0.1, negative 0.005, those are all considered small effect sizes. If your number for Cohen's d is between 0.2 and 0.8, then it's considered medium. So if you have a negative 0.6, that would be medium. If you have a positive 0.7, that's medium. Negative 0.35, that's medium, etc. Finally, if your Cohen's d is larger than 0.8, if the number itself is larger than 0.8, you have a large effect size for Cohen's d. So if it's a negative 1.5, if it's a 0.9, if it's a negative 2, those are all large effect sizes. Keep in mind that the positive and negative, or more so, don't let the negative trip you up. If just look at that number, a negative 1.5 is still a large Cohen's d because you're just looking at the number itself of 1.5, and that is larger than 0.8. This is an oldie, so I probably should update my memes on this, but whenever we have a p-value of less than 0.05, we are going to reject the null hypothesis. Those go hand in hand. We could also add a third person here and say statistical significance, and then boom, you got yourself, you know, the trifecta, or well, yeah, anyway. So here, we have a practice question because of course we do. So let us fill this out. Let's do this one. Let's do it all together. So this is going to be the whole thing. We're going to be calculating Cohen's d as well as determining whether or not we're going to reject or retain the null. So with that, let's get it cracking. Let me just erase my board. Okay. So you are interested in discovering if there's any difference between the average number of friends from the general population. So already I have the population mean and the population standard deviation. So I'm going to start filling that out. I have my trusty board over here, and I'm going to start filling out that information. So sample or population mean is 6.2. Population standard deviation is 2.3. And okay, so we have the average number of friends from the general population and Star Wars fans. Now their mean, their sample mean is 6.5. And we have 400 in the sample size. Conduct hypothesis testing to determine if you reject or retain the null hypothesis with alpha set at 0.05. Calculate Cohen's d as well. Okay, so first off, we have 0.05 as alpha. We know that. I've started writing out the null and alternative hypotheses. We haven't quite gotten there yet. Well, I have the critical value still at plus minus 1.96. But I have written out the information that we have so far. We know that our population mean is 6.2. The population standard deviation is 2.3. Sample mean 6.5. And the sample size of 400. Now, let's do step one. So step one for hypothesis testing is, of course, stating our hypotheses. So we're saying that the population of Star Wars fans, keep in mind this is our sample, our population of Star Wars fans has the same average number of friends than the general population. That is the null hypothesis. But we write that by saying, H naught, which is the H with little zero, where mu is equal to 6.2, which was the average for the general population. Now it says, is there any difference? You're interested in discovering if there's any difference between the average number of friends from the general population and of Star Wars fans. That's not saying, oh, do they have more friends or less friends? So we're going to have a two-tailed test because our alternative hypothesis is going to be not equal to. So null hypothesis equals 6.2. Alternative hypothesis mu does not equal 6.2. Step one, done. Boom. Now we do step two, which is where we are determining, we're setting a criteria. So we know that alpha is set at 0.05. And since we have alternative hypothesis of not equal to, we have a two-tailed test. Our critical values, since we have a two-tailed test set at the significance level of 0.05, we still have the critical values of plus minus 1.96, just like we did for the vegan problem. We know it's a two-tailed test, so when we find our p-value in the z table, we're going to multiply whatever we find in column C for whatever z statistic that we get from the next step. We're going to multiply that value in column C by 2. Since it's a two-tailed test. Two-tailed test, you multiply by 2 at the end. Okay, now let's go to step 3, where we are going to calculate our z-score. So we have the equation. Boom, boom, boom. And we also have all our numbers. So I'm just going to start with the calculating the standard deviation of, I've been saying standard deviation. I mean standard error of the sampling distribution of the means. Look at me, I made a big old mistake. I've been saying standard deviation this whole damn time. I apologize. So I'm going to start by calculating the standard error, my God. And that's 2.3, which was our standard deviation of the population, divided by the square root of 400, which was our sample size. So let's do that. So 2.3 divided by the square root of 400. That gives us 0.115. You can round that to 0.12 if you're so inclined, and I'm going to. So now we have our standard error. Now I'm going to calculate z. I calculate the standard error right here, and I'm plugging it into the formula for z. 6.5 minus 6.2, 0.3, divided by 0.12. Oh my God, no way. This gives us another z-score of 2.5. What? Let me just do that again. Yeah, all right. So our z is 2.5 again. Fancy that. All right. So we have our z-score equal to 2.5. And so now we can look at the z-table to find our p-value. Keep in mind that whatever we find in the column C for our z-table, we're going to double that since this is a two-tailed test. So let's go back to our z-table. Yeah, here we go. 0.0062 times 2. Oh, I remember this. P is equal to 0.01 when we round it. This is the same z-score that we got for the vegan question. So if you're wondering how I did that so quickly, it's because this is the same z-score, which follows the same, you know, has the same stuff in the z chart, all the same information. So our p-value is equal to 0.01 again. And we have our level of significance set at 0.05. Our p-value is less than that. Or we can look at how our positive z-score is greater than the positive critical value, so we would reject the null hypothesis all around. So we reject the null. So what does this mean? This means that the population of Star Wars fans has a different number of friends in comparison, has a different average number of friends. The population of Star Wars fans has a different You could also say that there is a difference between the average number of friends between the general population and Star Wars fans. That's fine. They both mean the same thing. Now, I threw my board to the side, but we need to calculate Cohen's d as well. Now, keep in mind that remember that the formula for Cohen's d, as we have right here, is, well, actually, right there, is sample mean minus population mean divided by the population standard deviation. So in order to calculate Cohen's d, we're going to just take our sample mean of 6.5 minus our population mean of 6.2 and divide it by our sample or our standard deviation of the population, which is 2.3. Okay, so 6.5 minus 6.2 equals 0.3 divided by 2.3. We have a Cohen's d of 0.1304347. So our Cohen's d, we're going to round it, is 0.13. Now, since we rejected the null hypothesis for this, since we rejected the null, we do have statistical significance, which means that we do have a significant effect size. Okay, so with that, boom, that's it. We've done it. Cohen's D equals 0.13. Now that is a small effect size. So we don't have as large of an effect size as we did here, as we did with the vegan problem. But with Cohen's D equal to 0.13, this effect size is considered small. When we look back at this chart here, oh wait, I missed it. It's less than 0.2, so that is a small effect size. All right. So that is our lecture for today. Pretty much the same thing. We've just added on measuring effect size. So we've just added on the calculation and interpretation of strength, small, medium, or large, for Cohen's D. Again, if you have any questions, never hesitate to contact me through email or come to my office hours or what have you. That's what I'm there for. So if you had any questions or if you had any confused look on your face when you were doing this, just hit me up and then we can figure it out for you. So with that being said, I hope that you've enjoyed this week. Sure, why not? But I hope that you guys, are doing okay with this material. If not, like I said, stop by. That's all I got for you. So like and subscribe.